Terrible trail.
Go on Yelp. Yeah, Glacier,
Okay.
terrible.
The campsite next to me was attacked by a grizzly 3 times in one night. So,
And then a mountain lion.
Yeah.
And we just went out that like the locals steal.
yeah. All the locals are rude.
Okay, so I want to discuss number 20 and sorry 20. I'm going to say 25. But is there anything before 25 that hopefully you guys have been diligently working on your assignment and maybe have encountered a question or two that you're like, this one I'm a little stumped on? Maybe any of the questions that are like, oh, so-and-so has this much angular momentum, so-and-so has this much, or maybe so-and-so had like a solid cylinder has the same angular momentum as a solid sphere, that kind of question. Or do you guys feel okay about that? Okay, well, and actually, let's look at 23 first, maybe. 23, we'll do 23 and then 25. So, so 23 says, so what if you have a point mass on a rod, mass of m, and it has an initial, the rod is a length of r naught, and it's going in a circular path with an angular speed of omega naught. And now, so it doesn't really say like this new length is r, doesn't say if r is bigger or smaller than r naught. So you can just kind of be general. Let's just say, for example, it got smaller, just for argument's sake. So the new r is called r, initial r was r naught. All right, so just being simple, what is going to happen when the rod goes? Say there's like a little spring-loaded mechanism in there where it can,
It's going to increase accelerate.
it's going to speed up, right? So does that make sense? Call this omega. Does that make sense? Okay, so what quantity is conserved here?
Angular momentum.
Angular momentum. What letter is that?
L.
L. So if you look at your formulas, you go, well, you don't have to write this out, but angular momentum. It's actually not a bad idea to write stuff like this if you're taking like a test. It's like in college, for example, that might get you a point. That's one, if you have no idea what the heck you're doing, you just get that 1 point for saying, hey, I'm pretty sure this problem is about angular momentum, so I write this sentence down. You get 1 point. Anyway, angular momentum is conserved. So you'd say, well, that means the initial angular momentum, L naught, is equal to the final angular momentum of L. So what's the formula for angular momentum? L equals I omega. But wait a second, I don't see any R's in there. So what I might have to do is go, well, for a point mass, how do I write I? mr squared. So what I really want to write is the initial angular momentum was m times the initial radius squared times the initial angular momentum. That make sense? Yes, no, maybe so? And then the final angular momentum would be the same mass times the new radius squared times the new omega. And what are we solving for?
The velocity.
The new angular velocity, the new omega. So first thing we notice might be cancely action. We go, okay, I guess it's fairly straightforward. It's just r naught squared over the new r squared times the initial. Which you might write that. You might find it more useful to write it like this. So it's, by what factor does omega change? It changes by the square of the ratio of the radii. Make sense? So if this was saying say it was a 2 to 3 ratio, the omega would change by a 4 to 9 ratio. Said a different way, if this R was 2/3 as big as this R, then the new omega would be 9/4 as big. Make sense? Okay. How about the linear speeds? This one's a little weirder. So, what's the relationship between, say, omega and the linear speed? Right? So anywhere I see an omega, I can replace it by the by the V over the R. You feel okay about that? So watch what happens. We can start with this formula. This is a nice relationship, right? But if I replace that omega with V over R, and then I replace this omega naught, with V naught over R naught. Does that make sense what I'm doing there? Let's simplify that a bit. What's going to happen? Let's see, what's going to happen when I have R squared? I mean, I could write it like this. Like, I could go R naught squared over R squared. And then I could send this R to the top, multiply both sides by R. That makes sense how I went from there to there? So what's the final answer? Does that make sense or no? Kind of an interesting result, It's like, for example, if you cut R in half, so if this was half as big as this, then the omega would be 4 times larger, but the V, the velocity, would only be twice as big. So, surprising, or maybe a little bit? And that's because, you shortened. Yeah, you're getting a 4 times bigger omega, but your R is also smaller, so your V is not as big. Brandon's upset because he didn't play the games. It's okay. No, it's Monday, just a few more days. Okay. A week later. Okay. Patience. Patience is key. And then C, what determines whether the ball will speed up or slow down? Very simple answer to this question. Yeah, sorry, this is where the printer failed me. Or I failed the printer, one of those two. What's a concise way to write this? The answer to this. So you know the answer, right? If this R is bigger than this R naught, it will slow down. If this R is smaller, it'll speed up. So you can write that very concisely, like you could say something like R being smaller than R naught would imply a speed up. And R being greater than R naught would imply a slowdown. That make sense? Nice. It's a nice short way to say it. Okay. Part D. Bigly question.
You want to take this whole page?
Huh?
Don't take this whole thing.
Yep. To take all this. No, it's not. Is anyone feeling brave and wants to answer this question? What was the torque exerted on the system?
I don't think it's. I acceleration.
That's a good point. It's not gonna unlock the answer for us, but that's definitely a good starting point. Maybe you look at that and go, okay. But it gets a little complicated because you go, well, wait a second. There was some angular acceleration, right? Like, as the rod was contracting, this would be, the omega is increasing. But aren't you also, so say this is a number, you also have the I value changing at the same time. So it's going to be, this formula is not really working if I is changing. This formula, the way we derived it, it only works for like a solid object that's not changing shape. So maybe this is a better way to think about it. Torque times time equals the change in angular momentum, kind of thing, maybe. What was the change in angular momentum?
There wasn't.
Huh?
There wasn't one.
Exactly. Right? You guys hear what she said? There wasn't a change in angular momentum. Angular momentum was conserved, right? And it's because, well, look at the system. Was there any, here's the system. Was there any external torque that could have been happening on this guy? Nope. Also, think about the forces involved. Where's the only force that was getting exerted on this ball? Well, it was a radial force. There was no tangential force that would exert a torque. So anyway, this is 0. So what was the torque?
0.
0. No torque. Kind of weird, right? So let's move on. This idea is really important. It's not easy to wrap your head around. This idea of like determining what's the system, what kind of system am I talking about, and from there going, well, could there have been an external torque or not? Because it's actually, if you're wondering, well, wait a second, this isn't sitting quite right with me because I'm like, if you're thinking, well, from the ball's perspective, didn't he speed up? So if you asked him, he said, hey, so if this is the system you drew, you just were focused on the ball, then there is an external force, isn't there? The rod, right? The rod pulls the ball inward, causing an acceleration. So it's all about perspective. It's all like, what are you considering as your system? Does this make any sense?
Yes.
So anyway, so if that's our system, you can see nothing can get in to affect the system. So, no torque. All right, let's do 25. How are our feelies? Feelies report, Henry?
Pretty good.
Okay. On a scale from 0 to 10,000.
Over 9,000.
Very good. Thank you. That's what I like to hear. Good. A plus. A plus.
See, Caleb, I would have missed it. Quality over quantity.
Oh, man. Caleb is quality and quantity. He's like Costco, large quantities, but they pick pretty good stuff to sell there.
Costco is like Montana's best employer.
Is it the biggest?
I think it's like, it's one of the biggest, and it has like the most general benefits of there.
It's good, dude. I like the company, but I hate the building. I don't like being in
Yeah,
there.
it looks like a horrible socialist person.
I hate how
It just scares me. There's just so many things in there.
concrete.
It gives me a horrible sense of dread.
There's a car parked in a building next to a food court. It kind of.
There's a car in there?
I feel like there's like a wall of tires or something.
No,
It's
their
like a
food
fever
is good though.
Energy. Energy.
That's not, yeah, look at the tires. Where did they come from?
We're just thinking of the tire tree.
The tire tree.
Has
Okay.
anyone bought Costco tires before, or do they just exist?
I think.
No.
Yes.
Because they're Costco.
Yeah, like your grandparents do.
Yeah.
That is. I don't think it's a perfect circle, but it's a nice
I
circle.
invest my.
Thanks, Trenton.
From there.
So 25 is 25 is hopefully 24. I hope is a pretty easy question. You just write. You might have to look up what's the I value for a solid cylinder, but 24 you just start with L equals I omega, and you substitute in for that I, right? You know the formula for a solid cylinder, and then you replace the omega with in terms of the period. So if you get stuck, we can go over it, but I think that one should be pretty easy for you. Okay, so this is an interesting question. This is a good one. I have a carousel, like a spinny disc thing. It's free to rotate. This is an overhead view, bird's eye view. You have a 20 kilogram RC car, remote control car. It's initially at rest. And then the disc, this is a solid disc, carousel, is 100 kilograms. And it's free to rotate. The radius is 3 meters. Okay. So the question says if the RC car starts driving around the carousel at a steady rate of 1 revolution per second, which is pretty fast, at what rate would the carousel have to rotate? Do we understand the question, like what it's talking about? So let's say this guy's driving around the perimeter. For simplicity's sake, we're going to say his radius of travel is 3 meters. Okay. First idea that I want you guys to think about would be that. This is my system, at least initially, I think about. Are there any external torques acting on the system? No. Any? In real life, it might be some wind or something, I don't know. Some wind, someone holds a magnet over here, or some kid walks up and pushes the carousel. Those would all be external torques to the system, but closed system here. And so what I can do is I can say that angular momentum is conserved, right? Yep. So my initial angular momentum is equal to my final angular momentum. All right. What was the initial angular momentum of the system before it started moving? Think simply here. The car is at rest. The disc is at rest. Zero. No momentum, right? Everyone understand that? Okay. Now my final angular momentum. Well, suppose I treat this car like a point mass traveling in a circle. Suppose I call this direction the positive direction. And the disk is going to travel in the opposite direction. I can call that a negative.
So it's still going to be zero if they cancel each other out. The
Yeah.
energy is conserved, or the momentum is conserved.
Yeah, but there's going to be a positive and a negative number that have to be the same size. Is it going to be we can solve? 3.
With 3 times 20
Well, let's just
minimum.
Yeah, what's gonna be the car? So the L, well, here. The L value for the car, so I can just write this here, I'll say L for the car plus L for the platform. Right? That make sense? They each contribute to the system. So the L for the car, now remember, we are treating him like a point mass. So it'd be, here, I'm gonna show my work so good here. See what I'm right here? It's a little overkill maybe, but so L is I omega. His L is his I times his omega. Right? So the I value for a point mass is mass times radius squared. And what's his omega? How many radians is he traveling if he makes a full rotation?
2 pi.
How long does that take him?
A second.
So his radians per second is he traveled 2 pi radians in 1 second, right?
It says right there.
Oh, yeah.
Makes sense? So you could have gone like this. You could have said, oh, his period is 1, which means his frequency is 1, which means his omega is 2 pi. It's the other way. If you know your relationships, hopefully you do still. For a solid disk, what's the I value for a solid disk? It's okay, you don't have to memorize them.
So,
1/2 m squared.
1/2 mr squared. See what I did there? 1/2 mr squared. Make sure to use the disk's mass, not the car's mass. The disk has a mass of 100. And then that's what we're solving for. But I do have a little bit of a problem here. I need to think of this as being a negative number, or this one. It doesn't really matter. One of them has to be treated as a negative number. I mean, because they're equal and opposite, right?
Yeah.
Clockwise and anti-clockwise have to once. Usually, you know, at least in math, this would be the positive direction. On our good friend, the unit circle, our best friend. We love him.
He's there.
So what do we get here? We get 20, so 20 times 9, 180 times 2, so we get 360 pi is equal to 450?
Yeah.
Check my arithmetic there. So it turns out that omega p, the omega for the platform, those are both divisible by 90. That's pretty nice. 4 pi over 5, I think? That's right. Radians per second? Yeah? Now, why would I write it? Why wouldn't I just have this calculator tell me it's 2.8 or whatever it is? Why is this superior? It's exact, yes. And it's going to answer the question in a bit more, in a way that makes a little bit more sense, I think, because the way the question's phrased is, at what rate will the carousel be rotating? Well, I can convert this into a frequency or a period, right? So what's the frequency then of the platform if the omega is this? Divide by 2 pi, right?
Yeah, so it's
Because omega is 2 pi times f. So if you divide that by 2 pi, what do you get? Guys, please. It's 2/5. Yes? Yes? Divide it by pi, you get 4/5. Divide 4/5 by 2, you get 2/5. Okay, so the platform is making 40% of a revolution per second. Or maybe you could say, oh, it makes a, it takes 2.5 seconds to make a full spin. Reciprocal.
Oh, no, I was thinking, sorry, because it gave us that it's gonna be 1 second per full, like, rotation around. And then your T value is greater than 1 second.
Yep, so in 1 second, the car will have made a full rotation around, but the disk will only have made 2/5 of a revolution in the opposite direction.
Oh, yeah.
And that's a little confusing to you. Imagine, because if you're thinking, it's reasonable to have this thought of like, well, shouldn't they just rotate at the same speed? But wait a second, what if this disk was 1 billion kilograms? What if it was like for effectively infinite mass? Would you expect the car just to roll around like without moving the disk at all?
Mhm.
You know, it's like when you push something. If I push a 50 kilogram block, if I'm on ice skates and I push a 50 kilogram block, we're both going to move. But if I push a 50,000 kilogram block, then I'm pretty much just going to be the only one that moves. The 50,000 kilogram block's barely going to move. So the mass of the disk certainly affects the calculation. You can see the bigger this number is, the smaller this will be. Okay.
Like the Earth problem we did yesterday.
What?
Wouldn't that be the same concept as the Earth problem we did yesterday?
Yep, exactly. Correcto. Okay, we're almost done, guys. You seem sufficiently bored. I feel like I've done my job today. I feel like a job well done. But we got to cover the last 2 parts. This is going to confuse you, maybe. Does the RC car exert a torque on the disc?
Yeah.
The answer is yes.
And isn't it always when it's moving?
Well, the reason this question is confusing, especially as a follow-up to the previous question, is we're like, wait a second. Here's my system. Now let's answer a different question. Is there a torque on the system? No. Right? But it says, does the car exert a torque on the disc? So then you change your perspective. You say, well, now the system is the disc alone. So if you ask the disc, hey disc, did you have any torques exerted on you? He'd say, yeah, this car spun its wheels on me and exerted a torque on me, causing me to accelerate. And the math shows it too, because if you say, like take what Caleb said earlier, where he's like, well, I want to look at torque equals I alpha, right? Well, from the disk, if you're just looking at the disk by itself, doesn't the I stay the same? So if there's an alpha, there must have been a torque. Okay. Same thing with like, if you look at this formula, torque times time equals the change in momentum. If you're just looking at the disk, yeah, the disk went from having 0 angular momentum to having some non-zero angular momentum. So this is a non-zero value. This is some number, which means this must have been some number. So, anyway. And then when does the RC car exert the torque on the disc?
Anytime it's moving.
Not quite.
Just that, would it just be initially, since it's a constant speed?
Yeah, initially when it's accelerating. So the moment when it's going as long as it took for it to go from rest up to that speed. Because what's his speed? Well, his speed is however fast you got to go. You can calculate the speed if you want it. It'd be V equals omega r. The omega was 2 pi. The r was 3. So that's roughly 19. Yeah. So it probably took a couple seconds for him to get up to that speed. It's pretty fast. Okay. So it was during that period of acceleration that he was exerting the torque on the disc. Because once he hits that final speed, they're in equilibrium, right? There's no more changes. You're gonna make it, Bailey. Don't worry, bro.
It'll be a long day.
It's gonna be a long day. Why?
I didn't get nearly enough sleep last night.
That sucks. That sucks. Okay,
Also my own fault. It's not important.
last question. Explain why the angular momentum of the car disk system, notice there it says car disk system, is conserved. You just need to make some sort of statement about how, when you consider this system as a whole, there's no external torque. It's a closed system. That's a good word to use, closed system. In order to have a valid answer for this, you need to have certainly the phrase, no external torque should be in there. There cannot be any external torque acting on the car disk system. Or you could talk about how all the torques involved are internal torques, right? The car exerts a torque on the disk, and the disk exerts a torque on the car, Newton's law and everything, Newton's third law. But there's no torque coming from outside the car disk system, okay? All right, man. Job well done. Looking at your faces, I see the